go to the YouTube channel.
It's been scheduled for the last 5 minutes.
Okay.
It's waiting for you.
It's waiting for me. I think it's stopped waiting. Surely by now.
Oh, it's
Okay.
Walk into it.
I think it's alright. I'm just going to. Audio is alright?
You can hear all of us.
I do see a problem that I forgot to actually put. My bad. I actually forgot to put the webcam on this one as well. My bad. Alright, let's put that in. Wait, which one is it here? Okay, which one? It's me. It's crazy. Insane. Okay, sorry if you're waiting online, which it doesn't look like anyone is, but or if you're watching this recording, just skip to the part where I start yapping about how much I love analysis. Wait. What is this? What happened here? What? Remove this. Okay. Sorry guys, sorry. I'll fix it up. What is it? Is it different? There we go. Okay. My bad. Alright. No, this should be full screen, shouldn't it? Let's put this as. Let's make this background. Oh, go. That's true. It's not open. That's true. Why is it?
It's a bit of window capture of sources.
Yeah. What? Okay, what? No. Huh? Okay, if I minimize this. I'm gonna move it here. Somewhere here. Oh, wait, no, I need not window capture, screen capture, that's the problem. Okay, we're going 4 minutes. Oh, look at that, we have 2 viewers online. If you have any questions before we get started, please.
That's just me.
Oh, okay.
My devices.
Alex, my G. Okay, where's screen capture?
It's just more than like you, it's more than live chat.
Say hello.
It's live chat disabled.
Oh, wait, is it? Shouldn't, it wasn't last time.
Well, that's just fine. This is laptop.
Is it just the laptop?
Yeah, mine's oh, it's because this Gmail doesn't have a YouTube account, so I have to create one.
Oh, okay, well, alright. Let's get started. Alright, we're pumped. Okay, ignore the technical difficulties. We're getting started now, nothing else counts before that. Today we're doing analysis. If you prefer the algebra half of the course, then you can watch the video on that from yesterday. But if you're like me and prefer analysis, then we're going to be going through that today. We have a lot of slides, so we'll be speed running a couple of them. But in the next 2 hours, I'm Luke. I'll be presenting the analysis side. So I'm a big fan of analysis. I wouldn't say I'm the best at analysis, but I enjoy it, so I think that may be enough. So we're going through all the topics that are covered in the course, I guess, including the prime numbers topic, which is never has like 0% likelihood of showing up in the exam. If you missed this yesterday, please sign the QR code for peer mentoring so you can support those naive first years next year and then journey at uni, so you can develop your mentoring skills if you're into that. Also, if you dislike how we're running these seminars and you want to see improvements next year for your second year or third year courses, whatever that may be, please leave it here. Whether that is in regards to what courses you want to see have seminars next year, or what structure you would like to see in these seminars. You can leave your feedback there. So if you want like third year pure math seminars, I might come back to academics next year. But otherwise, there's no interest. So if you're interested, you can sign up there. Okay, so we're going to the actual first topic now, enough QR codes. So for everyone who's here in person, that's the third QR code. I've had the attendance for as well before. Okay, so we're starting off with big O notation. So big O notation is a way for us to describe how a function grows in the long term. So we have this definition here. We say the function f is big OG when asymptotically f is bounded above by some multiple g, or specifically in terms of the absolute value. If you're familiar with computer science, you might see this in the context that doesn't care about absolute values. You assume functions are positive, but when you're dealing with functions that may be negative or positive, you care about the magnitude of the function. So you're saying that f is bounded above and below by some multiple of this function g, which you're assuming, like the absolute value g, which is like the envelope version, some sort of multiple. So you're saying it's growing no faster than g in the long run. And I've just almost broken the mouse. Okay. So we have a little question on this. To start off with, we want to show that this expression from the 2020 paper is big O of x to the 2020. Okay, so what we want to show is that this expression here is less than or equal to some multiple of x to the 2020. Specifically the absolute value, but as expressed in this might as well be positive. So what we could say here, looking at each term, if we make a step-by-step comparison, obviously we can say this one is less than or equal to 1 times x to the 2020. For this one, that's less than or equal to 1, because sign is always bounded above by 1, and that would mean, we'll get back to that one maybe, and then for large enough x, ln x is less than x to any power, so we can say that, we'll just leave this here for a second, and then since on this step we're going to gloss over a few details, you need this to hold for when x is sufficiently large, so greater than some a, so we quantify what that a is here. So when x is greater than 1, then we have this 1 is less than x to the 2020. Hope that's pretty reasonable to say. And the intersection of x and ln x, what's that? It's e to the x equals x, and that's some sort of mean value. Similar to the mean value theorem comes from the mean value theorem. You can say that that is true when, I think it's always true, because you know, I think e to the x is always greater than to x plus 1 when x is greater than 0, which is equal to x. So this would be true when x is the 2020, assuming x is greater than 0, such that it's greater to, less than equal to 2022, which is the other year we actually have an example of, x to the 2020. Okay. And since that by definition, our big M being 2022 shows the upper bound. Okay. So hopefully looking through the slides, I did that correctly. They also get 2022, or they just, a whole bunch. Okay. So they did like this, I suppose, which is also valid. You can also do it a bit abstractly, like saying there has to be some sort of M3, because you can say there is some sort of M3 because this equation would hold, because it is true that as x approaches infinity, that's not the right infinity, x ln x over x to the 2020 approaches 0. In other words, that this has to hold for some sort of m when x is large enough, and you can make similar arguments for m1 m2 based off these. Basically just breaking up into term by term so that they don't grow any faster than x to the 20, so they're slower than that polynomial growth. Okay? So little o is very similar. So little o is still, we're saying, it's bounded above by g, but it's essentially saying instead of less than or equal to, it's equal to strictly less than. So you kind of have the strict inequality where you're saying when it's like well defined to divide by g of x, you're saying effectively f of x divided by g of x approaches 0, like we've written here. That's when it's well defined to say divide by g of x, whereas this is a bit more precise definition where say g of x could be 0, even though this makes no sense when g of x could be 0, I suppose. But for sufficiently large x, you want this to be true. Okay, so you want g of x to be strictly growing faster than f of x, so that it dominates in the long run, and when you take that quotient, g of x squishes f of x down. So it's a strict other than, for instance, if f of x was f of x is equal to x, then g of x could be equal to x to the 1 plus, say, 1 over and in that case, it's true that this holds. Alright. Okay. I think that's comfortable with everyone. Yeah. So just picking up in that. And then big data is another one we need to know. Big data is saying that instead of growing strictly less than or no greater than, we're saying it's growing exactly like g of x. So here we have both an upper bound and a lower bound. In this case, you might see the notation that what this left-hand side here is saying is that f of x is as well omega g. I believe that's strictly in course content, but that's saying that it has g as a lower bound, and this is saying has g as an upper bound, but talking asymptotically in terms of a scalar multiple of g. So this is saying that in the long run, f of x grows exactly the same as g of x in terms of absolute scalar multiple. Okay, so like if you zoom out, the graph's going to look exactly the same. Just like one might be above the other, I suppose. But they have the same skeletal shape in the long run. Okay? And that's saying specifically that because you want to have the scalar multiple, if you like divide, then you have this lower bound m on one side, upper bound m2 on the other side. So you're saying that f of x over g of x is bounded between two constants, and so you're saying that the limit approaches a non-zero or non-infinity number in the long run is what we want. Okay. So that is pretty good. Any questions? Excellent. Okay. Oh, and this little notation of the... Did I have it here? Oh, no. On this slide we have the little equivalence relation where we're saying that f is equivalent to g if specifically this limit that we talked about, where we're saying that it's a little subset, I guess, where f is big data of g, specifically in the case where the limit is 1, then it forms an equivalence class of functions, because you can say that it's going to be transitive. If f is equivalent to g, g is equivalent to h, then it's going to be true that f is equivalent to h because f over h is equal to f over g times g over h. Both of these are going to approach 1 since this assumption, so the whole thing's going to approach 1. So it forms a lovely, nice equivalence class to say that the functions are effectively the same thing in the long run. So like one could be f of x equals x, and g of x is equal to x plus 1. They're going to be the same in the long run. And that's what we look. So here's a little cheat sheet. If you want to remember, that's just revise anything we talked about in just a concise limit form to think of it, in terms of limit 0, not infinity, and so forth. But it's probably better to remember like the precise definitions, because you might run into trouble when dividing by 0, but don't worry too much about that. Just in the long run, you're assuming g of x is not 0, otherwise, trivially it's not true. Okay, so we have a little question here that we'll briefly walk through. So we have a rational function of polynomials. We want to prove that, so degrees of each polynomial, we have degree p, degree q. We want to show that f of x is asymptotically big data of x to the n. Okay. So what we want to like the intuition behind this is that P of X in the long run is going to be effectively acting as a, I should say, like P of degree P, like the leading coefficient, times X to the degree P in the long run, and Q of X is going to be asymptotically, so this is like coefficient in front, likewise here we have Q degree P, I don't know where I put that there, degree P, degree Q, X to the degree Q, such that asymptotically what happens is that in the limit this quotient becomes the quotient of these two, since they're effectively what the polynomial acts like in terms of limits, and so you're just going to be dividing X to the degree P minus degree Q, effectively. It's like the intuition of what's going on, and it's just be some sort of constant. It would be slightly more rigorous than that in terms of what you have to write up, because we do want to prove it's big theta, so lower bounded and upper bounded. And you could try to work through the details of that. I guess like the hardest part is something similar to what was talked about in lectures, which is if you have a polynomial of degree n, then the let's just say polynomial of degree n, actually not degree, let's say n, because I'm not confusing here, then let's say h of x, then h of x is big theta of x. And I suppose you could use that to prove this here. If you apply the definitions of theta of x, and then that would give you the upper bound, so let's you want here. Otherwise you can do it how they have written here, where you do that little trick from Math1A, where you divide by the highest power, not the highest power, sorry, but the highest power. I'm pretty sure this is assuming, though, did you realize here? Oh, yeah, so since it's a rational function, you are making the assumption that, pretty sure n is greater than q. Come back to that. But what they do here, they divide by the highest power on the denominator, and so you have everything here. In the long run, this is going to turn into bk, and then here, it's dominated by this term, that's like the highest, fastest growing term. Okay. And so what happens? Yeah, I suppose it doesn't matter if it's degree P is greater than degree Q. What happens in the long run is that it effectively acts as this term here, because everything else is insignificant compared to that one. There's another intuitive argument you can make. And so what we are all left with is that f of x is going to be with this equivalent relationship equivalent to this, and so that proves that it is going to be, as we let m here be the degree of p, it's going to be big theta of x to the n. We said n was m minus k in the second slide before this. Okay. Yeah, so I guess that's a rigorous argument. I think you could also make a rigorous argument from what we're talking about here as well. I guess hard part you might want, if you have like extra time in the exam, try to prove this little lemma, which gives you the result for free. Otherwise, I think this is a bit more strong proof than that, I suppose. You'd have to argue this result for sufficiently large x. But the looks of the question doesn't seem like you have enough time in the exam to argue too rigorously. You just want to mostly supply intuitive reasons as to why it's correct. Mainly talking not only about the upper bound, but also the lower bound, using say something like the equivalence relationship here, or the big theta in terms of P and Q, how those interact with each other. Okay. Any questions? Okie dokie. Alright, so moving on to my mathematics directive's favourite topic, inequalities. So inequalities are quite fun, though some of the questions, I guess in some exams can be on the Olympiad level, but I think the content for inequalities is quite nice. Talking about convex functions, and also hodlers in inequality, which shows up in norms, which is pretty cool. So some basic inequalities are the triangle inequality, which you've seen many times, shows up in norms again. integral inequality and the sum inequality, where you bring out the maximum from the sum. Which is quite nice, pretty intuitive. Like you're saying, this is no greater than if x was its maximum at every single term, so you can factor that one out. Same intuitive idea holds for this integral, where you're saying this is integral here is no greater than if f was its maximum as you're integrating over g all the time. I think we're good for time. So moving on, some other notable inequalities. Hopefully seen this one if you've done for your math too many times. There's the AMGM inequality. I think we have the generalized version. Yep, on the next slide. We'll look at that soon. And then one of the most cool ones is the Cauchy-Schwarz inequality, which says that the dot product of x and y effectively in Rn is going to be no less than the norm of x multiplied by the norm of y, which is a pretty nice result when you want to talk about dot products, which shows up in the polar of a complex body. It's very nice to make that comparison to how large the vectors are like this, to be able to compare different norms together, and that's why the dot product is nice to nicely use the defined norms. We'll explore on a later slide. So we have this little question, a theorem here, sorry, which is asking us, or telling us that this is true, and then we're asked to prove it with this, and this question. So this is the generalized version of the AMG inequality, assuming that these are all nice variables that are positive. Then we have that the geometric mean, you can imagine like in terms of multiplying them together, you're saying you're trying to find a number such that this is equal to some number, let's say x, such that x is equal to this. So in other words, x to the n is the same as multiplying these all together. If you just look at this, that's like what you mean by mean in terms of multiplication, and this is the arithmetic mean in terms of addition, where you're divided by. Likewise, it's the number such that if you have that number multiplied n times, it's the same as adding this up. Okay? So we have this theorem that tells us that geometric mean is less than the arithmetic mean, with equality if and only if all x, k are equal. And what we want to prove now is that this is correct. And Lilkin tells us to use Jensen's inequality. So Jensen's inequality will be on the later slide, we'll go through it later. But what Jensen's inequality says is that if a function h is convex, then h of your sum, actually it would be the sum. You would have to have scalars that add up to 1, I'm pretty sure. Let's see if I can write it out and then make sure I get lambda later. You have lambda I times your xi. So we have h of this is less than equal to sum of, it's just sum over I, implicitly saying I from, let's say 1 to n, just to be clear, it's finite. Sum of lambda I times h of xi. Okay? So an example of a convex function, we'll explore what convex means later, but just take my word for the fact that negative log, and we're mentioning log basically just make it nice, but it works for any log with a reasonable base greater than 1. This will hold, greater than 1. So this will hold, assuming that sum of lambda I is equal to 1. So I'm just going to check myself to make sure that's right. Actually, I think I did instead. You need to divide by the sum here, don't you? What's happening here? Okay, not bad. You need to normalize the sum. You have to do... Actually, no, that's fine. There's an equivalent way of writing it, though, because you can say, yeah, this is an equivalent way of writing it. In this case, your lambdas are just your lambda I is equal to your AI over your sum of AJ. Just to say, like, this is the way you write it without that condition forcing them to be, the AIs to be, sorry, the lambda to be normalized. It's an equivalent way to write this. And there's a little definition of what a convex function is, where it generalizes, this definition generalizes to Jensen's inequality. We're saying what this intuitively says here, and this is going to relate to, I'll go through this just quickly, if you have points x1, x2, on, say, your, since this is a function from R to R, this is a point on your x-axis, we have f of x1 here, and f of x2 here, a function that was something like, what are these colors? Okay, green, my favorite color. Something like this, that would be convex. The reason why is because, similar to our definition of a convex set, which we'll explore later in the seminar, if you don't remember, it's saying that the, different color, what is this? That's a bad pen. I want more pens. I want different color pens. Okay. Sorry for the interruption. Okay, this is a better color. I want to move that. Okay. All is at peace with the world now? I think surely they were on time. Okay. We're saying that the, like with the definition of a convex set, the line segment from f of x1 to f of x2, which I guess you can parameterize with an t like this, that's always going to be in the region that's bounded below by the curve. So specifically, you're saying that effectively this black region here, that's above the curve, that's going to be a convex set. So that's how you define convexity for functions. If you want to link the definition of convexity for functions and sets together, that's what I found on Wikipedia, which is actually pretty cool. So no spoilers here, we're going to actually use this, assuming that negative log is convex, which is something you can assume. Negative log is quite a nice function, shows up in entropy if you've heard of that, and also we use it here quite a lot. So what we're going to do is say, given, I suppose we want to start with this product. Actually, do we want to start with the product? No, we want to start with the sum, right? That's like more indicative of what this looks like. So we're going to start with negative log of sum of our xi, which is what we have on the this side. And suppose we need the 1 over n. Maybe we should put that in. Okay, we can put that in. So Jensen's inequality says that if we have this type of convex function, h of this sum, that's something with this, but what we specifically need is this condition to hold. So we need to divide by, just divide by the scalars, 1 over n, sum of 1, which I'm realizing in this case is just 1 anyway, so I didn't even have to do that, but okay, just say negative log, but just to make sure you don't carelessly lose marks in the exam. So implicitly these sums are all from I equals 1 to n. This is going to be less than or equal to, did I actually remember? Yeah, sum I over I of 1 over n scalar times negative log of xi, and that's going to be equal to, you can use your log clause to turn your sums into products. That's going to be 1 over n times log of your product over your I, xi's. Okay, and it's still at the negative, so that tells us the negative log of your sum over xi's 1 over n is less than or equal to your negative 1 over n of your log of your product. And so what you can do, you can cancel out the negatives, so cancel out the negatives and then flip the sign, and consider that I might not get the sign correct in the end. And then you can remove the logs, because log is a monotonically increasing function, so you can do the inverse of that, which is exponential, to get rid of it. Oh, yeah, this seems fine. So this is the inequality we spoke about earlier. I in a step 1, I should bring this inside 1 over 10. So I did skip a few steps, but the details are all right here if you want to click and on what I just did there. Okay, And it looks like I did not blunder anywhere, which is looking all right. And we conclude the very nice result of the A and G inequality. So if you ever had to in high school, had the unfortunate time of trying to prove the case of A and G of n equals 3 or 4, and questioned your love of inequalities back then, this very elegant proof hopefully convinces you that inequalities are in fact very, very cool. So we went through this, we went through Jensen's inequality, the generalized version, which is generalized convex function. Young's inequality is something that shows up implicitly in inequalities we'll look at coming up. It's one that is introducing this P, 1 over P plus 1 over Q, which is 4 when P is greater than 1. We call, in this case, if we specify a P, then we call Q the Hodler conjugate. So this 1 over P plus 1 over Q case is going to be used to generalize Cauchy's inequality in terms of Hodler's inequality, and you can see it kind of shows up in this, maybe the first time you look at it, this might look a bit weird and not quite nice, but like comparing this to what this looks like is actually quite a nice inequality in my opinion. The way that you can prove that, am I going to do that on the next slide? No, the way you're going to prove this is you just use, again, your definition of convexity, and it should just be sufficient to use negative log again. So you'd be able to say that negative log of AB is less than equal to, I think I might have P and Q somewhere. I'll work that out later. Negative log A minus negative log B, and I'm realizing that's actually the problem, isn't it? What was I planning to do here? That was very silly. What was I planning to do here? Yeah, you can just slap it straight away. What was I doing? You have to in some sort of way use the fact that this is a 1. I realize now I have to split it up. Yeah. So negative log of AB, we'll figure out where, by looking at this later, where we put this. And it's because we have t here, so that t equals 1 over p, then 1 minus t is equal to 1 over q by this conjugate nature we chose. So this is going to be less than equal to negative log of a to the a over p minus log of b over q, like this. That looks good so far. But the problem is, of course, what we want to do with this here, this AB. Yeah. I suppose we could try to let make this like a xy, then what we could say is that this is equal to negative log of x minus negative log of y. I suppose we want to make negative log of x look something like, you're wasting time, a to the p, so you're saying that, that's not good, very nice, is it? Negative a to the p e to the parallel is equal to x. That doesn't look nice, that does. Okay.
This one should use Jason's inequality.
Jensen.
We can take lambda 1 equals 1 over p, x1 equals a up to p, and lambda 2 equals to 1 over q, and a2 equals b up to q.
I do see the vision. Okay, that makes sense. I don't know why I went such a tangent there. Yeah, so you're saying we use negative log of 1 over p times... yeah, I realized my mistake was I tried to start with this, where I should start with something that looks like more like a... Did you say a to the b or b to the p? Oh, b to the q. Yeah. Okay. And if you apply Jensen's inequality, or with this definition of x equals to this, then just going to pop out, isn't it? Yeah. Okay. I see. Okay. So you can say this less than equal to, skipping a few steps in x equals to, you should be able to see this negative log a times b. Oh, yeah, that's really weird one. Because when you use log laws, you can bring the p out. When you apply convexity, the p's cancel out, so you can bring in the ab together. Okay. It might be, like I said, a like analysis is not the best there. Okay, so since we spent a bit of time on that, we might skip over this question a little bit, because it's not too important, but the key idea of this question is trying to say, prove Jensen's inequality, but for the case of integrals, so the way that we have to do that is Jensen's inequality only works when we have finite sums. So what we can do is approximate our integral as finite sums and then take the equivalent. Specifically, namely, those finite sums are what you should be familiar as Riemann sums. And so we have to play around with our normalization of our lambdas there just to make sure it works. But if you do that, you should be able to see this intuitive inequality, just by generalizing what we did in the finite case, does also hold. So you can see little details of that there. And you should be able to have access to these slides afterwards, so you can review those in your time. And the hard details of what these lambdas that you want to make out of the delta x's, just to make sure it all lines up. If you make those one over n, it works out nicely, similar to the example of AG we did before. And yeah, it just all works out in the end. You take the limit of both sides. Okay, so the actually cool, very cool inequality that I spoke about before is called Lenz's inequality that says that this top product is less than the p norm of x multiplied by the q norm of y. So this is less than equal to xp times y cubed, which is very nice, assuming that p and q are both the conjugates as I spoke about before. And the proof of this is actually quite nice as well. I won't go into details here, so I don't trust myself anymore. The same also holds for integrals, which can be proved in quite a similar way. We can also generalize Hodler's inequality, which can be proved by induction from the original Hodler's inequality. To say that if you have the q norm of a product of functions, then that is the product of the norms of each of those functions, where 1 over r, in this case like we're replacing 1 here, like 1 over r, is the sum of 1 over a bunch of different q's, to say that it's less than equal to the pi norm of f. So if you don't remember what we mean by p norms or q norms, we'll go through that when we get up to norms, but that's just how it generalizes. Over here, we're going to be using that in the exam question over here now. So we are told, I guess we are just told this here, and we are then asked to prove what looks to be just applying this when we plug in 1 over 3. The other case, that's the only difficulty here is that this isn't quite the generalized version we saw here, rather it has this r specifically saying this has to be the 1 norm, or specifically less than that 1 norm, or if you're assuming that was then this is the 1 norm, where you're just taking the sum of all the values, or the different coordinates, absolute value, but in this case absolute value is just the value itself. What we want to prove is some application of this inequality. So you can maybe guess what we need to do if we just try to plug in try to plug in q equals p equals r equals 3, then you get very close to this, but the problem is that you have something that looks like sum of x to the k to the power of 3, likewise y to the power of 3, z to the power of 3. So what you do, since like the cubed root function is a bijective mapping for positive values, you can say like with Vowels generally assume that we're dealing with, instead of the number itself, we're dealing with its cube root like this. And so that means when you take the cube, it cancels out, and over here we get the product of the cube roots on the right hand side. We're just applying this, reducing it down to this case here, which hopefully you can see pretty nicely. Just a little application of it. And with that, we're done with inequalities now. Unfortunately, we're moving on to norms and convex bodies. Okay, so in terms of the definition of a norm, these are just a few reminders. So we need to be what's called positive definite, zero if and only if x equals to 0 and otherwise positive. It brings out scalars, so I guess the technical detail you might forget sometimes is that it brings out the absolute value of the scalar, where lambda is from your scalar field of your vector space. So norms are defined on vector spaces specifically, as opposed to something like metric, if you know what that is, which we define on a set that isn't necessarily a vector space. Finally, the triangle inequality, which we spoke about many times, which is very nice for us. It makes when you're doing your epsilon and delta proofs in your norm vector spaces, makes actually lets you work. It like provides the bounds that you need to prove something converges. Usually, it's very nice in proving convergence. What you kind of need in that case for convergence. Alright, so we have then the p-norm I spoke about earlier. That would explain this. The p-norm is what we do. We take the sum of xk to the power p, and then take 1 over p in the end. For instance, like you are familiar with, of course, the Euclidean norm, where p equals a half. That's the sum of over k of xk squared to the power of a half. Right? You've seen that many times in high school. It's like that would be the square root in this case. Yeah, it's like your x squared plus y squared, and if you're in 3 dimensions, it's plus z squared, and if you're in not R2 but R1. Okay, you have a few more than 2 there. If you're in Rn, then it generalizes quite nicely. Minkowski's inequality tells us that this does define an actually good norm, so it tells us that this is valid. You can prove this using a bit of algebra with sums, and then I believe one of the inequalities that comes from either Jensen's, Young's, or one of the other ones. Hopefully that doesn't show in the exam though. But maybe good to revise that, as well as the proof of positive inequality which I spoke about before. But it's it forms a valid norm. These ones are also pretty clear why it forms a valid norm. You assume p to be greater than or equal to 1, and you assume lambda to be. This property is true, sorry, because when you have lambda, you'd have a factor of lambda to the p, and then when you 1 over p, that just becomes the absolute value of lambda because you have absolute value here. I guess technically as well, p doesn't have to be strictly less than infinity. You can do some nonsense like this, which might make a few calculus teachers angry, but if you're working in extended real numbers which include infinity, that's fine, because what you can have is that I'll go over this later probably, but I'll be on the other side. P infinity is when you're saying it's the limit as p approaches infinity of this, which is related to what we did in the first question of assignment 2, which is the maximum of x to the p, because that's like the term that dominates, so everything kind of like is not significant when p approaches infinity. So it's just x to the p that dominates in that sum, and then we take the root of that 1 over p as the maximum over each k. And then the case where p equals 1, that's the L1 norm sum of the absolute values, which is the, also called the Manhattan. In the case where we're dealing with metric, it's called the Manhattan metric when you introduce a metric from the norm, unless I'm mistaken. Okay, convex bodies, we've read this before. It's a set where every single line segment between 2 elements of the set is entirely contained within this set. So it's a nice little, it's like if you've done complex analysis, it's stronger than like polygonally half connected, you need to be a straight line, so it's like stronger than that condition where there's like no gaps, there's like curves, there's like corners you have to go around to like travel through the convex body, where like the shortest path is just to go straight there, I suppose. And they're quite nice in analysis. For instance, if you're interested in linear programming, they show a lot of linear programming in terms of finite solutions. So another thing nice about them is that if you take a convex set and you consider the set of elements such that the norm, other way, if you consider a norm-vector space and consider all the elements that are less than or equal to 1 in terms of that norm, then that forms for you a convex set. Okay. So what this effectively proves for you is that convex we'll get to what a convex body is in a second, but what this effectively proves for you is that a norm can give you a convex set. Specifically, this set will be a bit stronger than a convex set. It will be called a convex body, and the converse will be true later on. I'll actually explore what that means, but this is like not useful yet because we don't know what that means. Okay, convex bodies, let me quiz myself. So convex body, a convex body is a specific convex set that satisfies three additional, depending on how you see it, a couple of different additional requirements. So the first requirement is that convex set, it looks, you can visualize it as just like a little lab like this. Actually, no, it needs to look something like in the artistic case, it looks something like an ellipse-ish. It can also be a bit different, like a diamond or so forth. The first condition is that it has to be what's called centrally symmetric. So centrally symmetric means that if you have a point, centrally symmetric means that if you have a point x in k, then its negative is also in k. So if this point here is in k, then its negative is also in k with respect to the origin, which is, I guess, the center of the convex body in that way to think about it. You can also say that a few other properties effectively say that it is a compact set, meaning it is closed and bounded. So closed meaning it contains all its limit points, and bounded meaning that it's contained of some ball radius c, and then so that's like it's bounded above, and also whenever you have some sort of sequence, you can always find that limit within the convex body. And then the final property is that it's also bounded below, so you can find some sort of ball that is entirely contained in your convex body. Okay, so that's how it's written above here. So you say it's bounded above, bounded below, by balls radius c, little c and big C. In terms of the Euclidean norm, this one's about the p equals 2 norm, and also we talked about how it's closed. You can also equivalently, in terms of analysis, there's two common definitions of a set being closed. One is that it contains all its limit points, or that its closure is itself. You need to know closure is the union of the set with its contact points. If you know what a contact point is, don't worry about that if you don't. Another one is that it's equal, its complementary is open. Okay, so there's different ways to. You can also say it contains its boundary, which is that idea of contact point I spoke about. If you're interested, search that up, otherwise it's not too important. Okay, so this question just wants us to prove what we claimed here, that this set is not only a convex, it's not only a convex set, but also a convex body, so it satisfies additional requirements. So to show that it is a convex set, what you're going to be using, like I said before, is this triangle inequality, which makes this quite easy for us to use. So the details there, and I'll show you in the next slide. But what we then need to think about is why this specifically is a convex body. So we need to satisfy these three requirements. Requirement 1 is pretty simple. So if the norm of x is less than or equal to 1, then of course the norm of negative x is less than or equal to 1, because we have that linearity, or the absolute value linearity. So this would just be like the lambda equals negative 1, means that its negative is also less than or equal to 1. In terms of it being closed, like kind of obviously the set is closed, I guess. So if you have, the idea is like if you have a sequence within this ball, it's going to converge, that converges, it converges to an element x that has its norm less than or equal to 1 as well. You can prove that, I guess, by saying you prove this in a different way, but the function, I have this on a different slide, f such that x maps to the norm of x, that's a continuous function. So that means if you have a sequence xn approaches x, then the norm of xn approaches the norm of x. Okay? So if xn is entirely contained within this set B1, then this sequence of numbers is always going to be less than or equal to 1. And so a sequence of numbers that's always less than or equal to 1 has to converge if it does converge, which we know it does here. If it does converge, then that number also has to be less than or equal to 1. That's a similar argument to something you might have done in your second assignment, unless I did the second question completely wrong, but that's a similar argument you might have done. And then finally we want it to be bounded below and bounded above by balls of radius c and big C. And that's a little more involved. That again actually does use this property that this mapping is going to be continuous. And so what you effectively argue there then is that you're looking for Euclidean balls of radius little c, big C within that space. So you're effectively saying that when x is in B1, you want the norm of x to be less than or equal to big C norm of x in Euclidean, less than or equal to norm of x in little c, sorry, Euclidean as well, little c here. So what this is equivalent to is saying that c is the lower bound of bringing this factor divided by it, assuming x is non-zero, x over x2, less than or equal to big C. So this here, this number, is a element of Rn that has modulus 1 with respect to the L2 norm. Sorry, not modulus, it's not cost numbers, but norm 1. Okay? So what you're saying is that when you map the unit disk, so the set of elements that have norm 1 in Rn through this function, then it is bounded below and bounded above. So it has to be bounded below and above because effectively you can act that that's going to be a compact set, and you're mapping a compact set becomes a compact set. It's a little analysis they'll have on another slide. And you can argue like it's bounded below because this never has zero modulus, so it has, you can use the properties of positive definiteness similar to like this argument we kind of made here. And it's bounded above because of the fact that compact sets match compact sets. There's a bit more to it that you can see in the lecture slides, but this. Don't have too much time for that. Okay, so we can just quickly explore what is done here though. So, like I said, to prove that it is actually convex, you use the triangle inequality like so. So you can split it up like this. Since lambda is positive by construction, you can bring lambda and 1 minus lambda together quite nicely to make it like so, which is nice. Using the property that I suppose you can say one of these two is less than or equal to the other, and both are less than or equal to 1, which is what you can use there. So it's not really like hard to prove this in terms of like this is quite a, I guess, weak inequality. You just apply your definitions and it turns out to be true. So this does occur. B1 is a convex set. Okay. As I spoke about before, you bring out the negative 1 to say that its negative is also contained in the set. Boundary. Okay, so it contains this boundary, so it's closed. I guess that's another way to argue it in terms of working with this norm. And what is going on here? I forgot about this part of the slides. So you can choose epsilon 1, epsilon 2, and you can look at when the norm of x is sufficiently small. You define your ball like this. So what you can then say. So you can argue pretty much that these balls would be contained within, with respect to this this metric specifically, so this norm specifically. So if you make like epsilon 2 as something that's greater than 1, and this is something that's less than 1, then you're saying that your set here is when the norm is equal to 1, or less than equal to 1. and say this ball is going to be when you're with some sort of ball strictly less than 1, and then this one strictly greater than 1, so you get that containment like so. So you're kind of claiming that. I did say here that these are Euclidean balls, raised C and big C, but you can think about the fact that you can kind of work the same way with balls from your other norm here. To be more precise, you have these Euclidean norms and make arguments like this. But since all norms in Rn are equivalent, then this is the same argument anyway. What I mean by what all norms in Rn are equivalent is that your Euclidean norm, your x2 norm for all x is less than or equal to some m1 for some specific, your specific norm for n equal to m2 less than or equal to for that's not 2. This is true for all x and for all norms compared to the Euclidean norm. All norms are equivalent, so you can make this type of argument. Okay, so this isn't like what these slides go over, like the brief intuition about widespread. I added my own special source to that, so up to you to make that legal. Some just quick analysis revision, talking about open sets. Open sets have every element have a ball. An open set effectively contain that element entirely within inside the set. It's closed if its complement is open, bounded if there's some larger ball that the set is completely inside, compacted if it's closed and bounded, as we talked about before, which is the Horion-Borel theorem. Path connected if for all points x, y there is a continuous function that maps, that has its endpoints being x and y from the interval 0, 1. Okay, and that's entirely contained within the set. Okay, and then just the important theorem for this topic is that convex bodies and norms are equivalent. There's a one-to-one correspondence between the two. The forward direction is saying, well, the argument we made kind of up here, just in more detail, is that you can define a convex body from the ball of, well, specifically it should be the ball of radius 1. So the ball with respect to that metric of radius 1, and then conversely, you can, if you remember from the exercise, you can pull a little bit of nonsense with this set Lx, and using the infimum of the set. The infimum is the, you can define it as, let's just say equal, is the greatest lower bound. So it's a number, it's a lower bound that is the greatest. A lower bound is a number less than all elements in your set, and you're trying to find the greatest one. I guess you could say it's like the, if you have the set an of all limit points, all lower bounds, then this is greater than to all of this. Okay. So that's how you can take the reciprocal of that infimum of Lx, like the smallest. You effectively find the smallest element when it's not true, and you can play around with the algebra, and it turns out that satisfies the triangular equality and a bunch of other inequalities in terms of like the scalar multiple, and also the positive definiteness, and also plays nicely in the fact that it gives a specific correspondence in terms of in this norm that you introduce, your convex body is exactly equal to the ball of radius 1 in that convex body. In that normed vector space. So that's the correspondence here. These two correspond. The convex body and its corresponding norm. Corresponds. There's a isomorphism where you're saying like you have an isomorphism phi that maps k to b1 of k. So one-to-one mapping between convex bodies and norms in that way. It's mapping k to it maps k to that norm such that that condition holds. Where, yeah. So that there's a little argument the end of the proof of this exercise that argues that this has to be true. Because I guess most of the hard part of the proof is proving this side, proving this side, but you need this to show that it's like a one-to-one correspondence, not that there is just like a correspondence in either direction. Okay, so continuous, continuous you can define as when your value gets arbitrarily close to your position, then your function gets arbitrarily close to where you say is the value of the function in that position. And so continuous functions have a bunch of nice properties. For instance, they preserve path connectedness and they preserve compactness, which is quite nice. So specifically, that's what we're going for this mapping that maps our value to... Yes, maps our value, our vector to its norm. That is a continuous function with respect to the Euclidean norm. So as we spoke before, talk about continuing this way, when we get close, the way we're defining it, get close enough to your value is in the Euclidean norm here. And also a corollary of this, as I spoke about, is that all norms in Rn are equivalent, which is a very nice theorem that follows from the continuity of this mapping, and also the fact that the triangle equality as well, using this theorem as well, which says that if this is true, if you get arbitrarily close to your value with respect to some sort of norm, then the norm of that value, the sequence, gets arbitrarily close to the value itself. The reason why that's true is because you can use the what's called the circle inequality sometimes, which you can prove from the triangle inequality that says that this is greater than equal to the difference of two norms in absolute value. You might have seen them before. Okay. So this is up and down by this, so if this goes to 0, this also goes to 0, so you have the emergence. The converse of this theorem is not necessarily true. Okay, so I did effectively talk about this one before. It is quite scary to see a question that asks you to prove that all norms in Rn are equivalent, given that's quite a strong theorem. I did basically walk through the details of how I would prove that using, again, the continuity of this mapping. An alternative way is presented in these slides, just to hand wave it a little bit in terms of talking about the balls of specific radii, which is how, if you watch the last lecture of this course, you can see that how that's talked about using convex bodies a little bit. So the way you do that, you can talk about convex bodies with, if you take two arbitrary norms and talk about the convex bodies associated with them, then since you know that they are compact, bounded above by some sort of Euclidean norm, you can make this argument, which you can translate in this way. Which is that you'd have to, I guess, technically involve the Euclidean metric in some sort of way, but to make this a bit more precise, but this is also true. I did kind of trip out when I saw this the first time as well, so don't worry, it is tripping you up. There are better ways to prove this result, but if you're in a Russian exam, just hand wave between using the fact that it's bounded above, bounded below, which if you're talking about balls or radius, you can talk about how like this B dash is this B dash is when x is less than equal to 1, and this larger circle is when this larger x dash is less than equal to a larger C1, and and you can use that. I don't think it's exactly C1, I think you might have to do 1 over C1, but that gives you an inequality that you can use. Because you'd have to, you can write this as like x dash over C1 is less than equal to 1. Yeah, so you're like comparing the size of the balls there, but yeah, not too precise. You can play around with it, and you can make the same argument by flipping around the roles of the norm and the dash norm, and so eventually you get the inequality on either side, with like the inverse of one constant. And it all just works out quite nice. I think we might take a break now. Oh, there's just one more question here. Okay, we'll just go through this quickly, then we'll take a break. So we are looking at a complex body. We want to know if AK is convect, where A is an invertible linear operator, so just an invertible matrix, multiplying everything. So so what we want to look at is it compact? It would be compact because this would also be a convex body. I believe that was done in the tutorials at one point, but there's also solutions on the slides. Basically, the convexity follows from the fact that you can, you can say that the linearity of A is what effectively gives you the fact that it is also convex, and then bounded above, bounded below follows from the continuity of this mapping. This A is a mapping of the operator. The essentially symmetric also follows from A being linear, and then finally bounded also follows from continuous functions bounded sets, the bounded sets, if they're also closed. So you're trying to prove it's closed, continuous functions closed if they are bounded. Yes, it is. So that's the spoiler of the answer. You effectively want to prove that AK is a convex set as well. Okay, by using continuity. Yeah, you can argue that as well. You guys don't have to go into that much detail. AK is compact, AK is also compact. So you just remember K is a convex set. Alright, so moving on. The Bolzano-Weierstrass theorem is something that's quite important in analysis. You don't use it too much here, you might have seen it in your assignment. But what it says is that if you take any bounded sequence in R, then it has a convergent subsequence in R. Okay? And it also generalizes to Rn, if I remember correctly. So it says that the generalized version of Rn is that it's sequentially compact. Meaning every sequence in S has a convergent subsequence, similar to how we talked about here. Compact, so compact is specifically what you need. So that's like the generalization how you talk about bounded, effectively. So you need it to be closed and bounded. You can also have like the, if you know a bit more about analysis, there's this word called relatively sequentially compact, or relatively compact, where it's closure is compact, where you're effectively saying it has this property where the only reason it need to be compact is because you need the actual limit to be within your set. So, like what you're effectively saying is that in Rn, R2N, if you have a bounded set, then you have a convergent subsequence that converges to Rn, and then if your original set S was also closed, it contains all its boundary points, so that limit has to also be in S. Okay, duality is quite cool, so we'll come back to that after this break. Yeah, for a little bit. And I realize we're probably not going to make it on time, but that's okay, because p-adic norms aren't too interesting, so we can sacrifice a bit of time on that. We will reconvene in 5 minutes. So if you're watching online, let me know if you have any questions. I think there are 2 responses. I can see 2 people said they are the same person. They love analysis, which is great. I also love analysis. Is that you, Alex? Okay. Let's pretend that wasn't the person I know. I'll leave this turned off. I'm going to turn off the microphone and return in 5 minutes. I really like the break slide. Where is the break slide? Oh, it's not here. What? Come on. Scroll. Break. Okay, break. Here we go. Yeah. I forgot how you prove toddler.
It's the stupid. It's and one where like you construct an average.
Oh yeah.
You construct AJ equals something.
And then you use Young.
It's probably Young.
Yeah.
Yeah, that's what we put Young.
You use Log. No, you use Jensen. You use Jensen. Yeah, because it's like you use no, you use Young's because you You use Jensen to prove Young's. You use Young's to.
Yeah, it's young here.
What those inequalities?
So it's just consequences of inequalities.
That's right.
Yeah.
Like it's pretty cool because it does relate to norms.
Got really funny.
Final exam question. Prove Young's
Fucking
exam
how
holders.
unfair was it that in the final exam they had to prove that all norms in R are equivalent in 2020? That's cool.
2020.
Yeah.
Wait, which year was it?
2020.
Yeah, that is.
So it was lockdown. No.
You just like it's over if you see that.
Was that lockdown?
Not sure.
2020 and 20.
That was T3
Yeah, it's lockdown, right?
T3 2020 December.
Oh, it depends on if the uni still had. They probably did, but like.
You guys for that theorem was pretty short.
Huh?
Because yeah, like the way I did it was like saying the rule of
We had stay-at-home exams.
Oh yeah, high school
High
was
school just-
locked down for a single
Oh, is that
term,
where
then
you
we
did
came
it?
back.
for the proof that the rules were equivalent, I made them all equivalent to the Euclidean form.
Yeah.
But that took a while.
See,
It's just
that was,
relative.
yeah, that was quite a short.
It boils down to the fact that the mapping, like I spoke about, is
Yeah.
continuous. So that's all you need.
So
Because you realize
today is a strict subsession attendance yesterday.
Wait,
strict subset. I see.
Are the slides going to be on at STEP?
Uh,
Because I saw the one that Osman.
they should be. I try to get my team to upload them. Yo,
How does mapping preserve compounds?
how does
Like
continuous mapping map compact sets to compact sets? Depends on how you define compactness. So in further analysis, if you do like higher analysis next year, you define compact sets as every open cover of your set has a finite subcover. And nope, that's not useful. Okay. Alternatively,
Is it the closed
you
endowment?
can use definitions because there is an equivalent definition of compact sets that I think only works in norm or metric spaces, which norm spaces are metric spaces, where you can say a set of compact if only every subsequence is bounded converges on set. I think it's like the converse of Rosanna Weisstrass I had before. Yeah.
So it's just
And you can say like continue, you can prove from definition that if like you know from like 1.8, you can prove from definition that if x approaches a, then f of x approaches f of a. If f is continuous, right? That's what you use to prove that compact sets. Yeah, that's how you prove it. How you prove what?
like have we proved continuous compactness?
No. Because you need like that more infrastructure of what compactness really is. Because you say compactness is when it's close to enough, but it generalizes when it's not.
So we're just being told.
You've just been told to trust the theorem, bro.
Okay.
Trust the theorem.
Surely final exam high analysis prove continuous mappings preserve compactness.
I would be walking out, I swear. I'd be dropping out actually.
I've dropped the course in the final exam.
It's all fun and games until they ask you to do that.
It's all fun and games until you go into the course.
It's all fun and games until you actually start studying. If you enjoy your stew back, then you don't have to worry about nothing. Okay. Alright. We will resume now and we'll go for a little speed run as all these MathSoc seminars end up being in the last hour because we get too comfortable in the first hour and we run out of time. How many slides do I have left? Okay. Approximately half. I should put on the microphone probably. Okay. So, thanks to a little helper. By the way, if you want to remember how to prove Hodler's inequality, you do so by basically normalizing your equation. You can do a similar thing to try and prove the Cauchy-Schwarz inequality. You like normalize it and you play around with it. So to prove Hodler, you apply Young's inequality based on the normalized version of it. But you can see that in the slides. We'll look at duality now. So duality is more and norm. So I guess there isn't too much of a good reason to do this in terms of looking at dual norms. I do know like one application of, I guess, do norms some sort of way, but yeah, in this course it's not much. Like you're told about why this is useful, other than it satisfies some very nice properties. So what we define the dual norm as is the dual norm of a norm like this. We usually denote it by a star. Is such that the dual norm of x star is the supreme of the dot product divided by the norm of y for all y in that y is not equal to 0 because you don't divide by 0. Equivalently, that's saying I like bring this in to the interior. This is y over y here. That's saying it's equal to x dot y, where y has norm 1, and so it's like saying it's the maximum of the dot product. Okay, and so this relates, as I said before, to Hodler's inequality in a major way, because we have that Hodler's inequality related to the dot product of x and y related to the norm of x with respect to the p norm, norm of y with respect to the q norm. So that's saying that that's like an upper bound for what this is when x, this is like the p norm. You do need to do a bit more work in terms of when they're equal to show that that actually is the supreme rather than just an upper bound, if you kind of get what I'm saying. But you can play around with it, and there's a little additional supplementary notes in the exercise for analysis. You can have a look at it, it goes through that. But what this really tells us that hopefully intuitively, by Hodler's inequality, the dual norm of the p norm is the q norm, which is very nice, where don't worry about that, that's a bad way of writing it, where 1 over p plus 1 over q is equal to 1, in other words, the Hodler conjugates of each other. Okay, so this is where math, the extended real numbers come into play. So if we want to find the dual norm of the one norm, you would say that that is applying like this definition. Don't worry about the fact that what we're about to do is a bit nonsense. We want 1 over p plus 1 over q to be equal to 1. In this case, p equals 1. This would be 1. And so just don't get scared. So 1 over q is 0, and so q equals infinity. Easy peasy. Factual. So in the case where we're dealing with the this is actually true, of course. When we're dealing with the case where we have the one norm, the Manhattan norm, then it still is the infinity norm, which is very nice. So the maximum we talked about before, and when we have an actual numerical answer, when you plug in 2 here, you get also 2, and so the dual of the Euclidean norm is itself, which is a very kind of nice property. Okay. Okay, cool. So what we're looking at now is if we have a convex body in Rn, then we define what is known as the polar of K to be the convex bodies associated to the dual norm. Okay. So we have introduced the dual, we've also introduced the polar, so there's just definitions. I think the hardest part about questions like this in the multiple exam is just remembering the definitions and remembering the dual, like, oh, this isn't a definition, but results like this. Okay, so yeah, the way you can find this little K naught, which we denote it as K naught is the polar body. We say that you can look at it like this. K naught is going to be specifically the set of y and r such that the dot product of x and y is less than equal to 1. The reason being is because if you do look at the definition of the dual norm and like the correspondence we say between polar bodies, convex bodies and norms, we can write this in terms of that norm, which is the same as saying, as we spoke about earlier, would require this to be equal to 1. Likewise here. So you're saying this is true for all x such that x is equal to 1. Actually, what am I seeing here? No, I'm tripping. I am tripping. It should be less than equal to 1. But it shouldn't as well, should it? This is correct. This is correct. What's tripping me out is that's equivalent to this, which is equivalent to this, and is supremum of x k x dot y over x to the k. So if this is less than or equal to 1, then... Oh, okay, I see my issue. So this, the norm of x is less than equal to 1 anyway, so it doesn't matter. So the reason why this should be 1, and then this is equivalent to saying x is in the convex body associated to that norm, because I was being silly. Okay, skip these steps. Because remember that we define k, well, like we have a correspondence between k and the polar radius 1 of the x k norm. Hopefully that makes sense. Okay, so convex, polar bodies, some results you can have is that like if you have a scale factor, then it's cancelled out effectively. Like it's if you have like a matrix multiplication, then it's the transpose inverse, if I remember correctly. Like the polar of we talked about before, the a times k, the polar of this is going to be a inverse transpose case, like you're doing the inverse of the operation, like transposing it to like change between your domain and codomain, I think. But that's assuming you're an Rn effectively. So in this case, yeah, if you talk about ball of radius 4, then it's going to become a ball of radius 1 over 4. So ball of radius 2 becomes radius 1 over 2. You can prove that quite easily just by using the definition. Here, just making it equivalent and so forth. That's not too difficult to do, usually. And what else is there? Not too much else. Oh yeah, and an ellipse, like you're saying you're kind of flipping around the axes for an ellipse. Okay, so we'll see an example in action now. So for this one, we want to find the polar of k, where k is given by this. So what we want to say is we want to find the k dash is equal to the set of x dot y such that less than equal to 1. It's for x in k, so we want such y that this condition holds. In other words, it's saying x1 dot y1 plus x2 divided into r2. So we'll do this by definition. First, you can apply like that theorem we talked about, get this result if you want to, but we'll just try to see if we can work it out by definition first. So, what we can say is that, at least by the Cauchy-Schwarz inequality, so I see actually there's probably an algebraic trick we want to do, because we want to make a comparison between this. We could say that this is equal to, like if we bump up x2, 2x2, and bump down y2, like this, what's going to happen is that by Cauchy-Schwarz inequality, this is less than equal to norm of x1 and then 2x2, and then y1 and then y2 over 2. So this is less than equal to x1 squared plus 4x2 squared, square root. And then this is y1 squared plus, so now we're just like it's dividing by 4 now. 2 over 4 squared square root. By definition of our convex body, this is less than, convex body, this is less than equal to 1. So less than equal to just this, the y1 squared plus y2 over 4 squared. Okay, so it is then a sufficient condition for this to be less than or equal to 1 for this y1, y2 to be within the convex body. And you can probably prove the other way as well, that is also a necessary condition, because remember, like proving this is like an upper bound, you need to be a bit more precise. You can prove as well that if you have an element that has to satisfy this equation, and I have forgotten how to do that, so I'm just going to cheat off here, and it doesn't tell me, does it? Okay, sure. Yes, so I guess it's just applying the little theorem we talked about. And so this should be all fine, except what did I get wrong? There is a 4 here, and there is a 4 here. If you're saying this is less than 1, then that's equivalent to bringing the 4 up here and 4 on the 1 here. So this is equivalent to saying this condition holds, if you can see that. Okay, so the next theorem we have is quite actually hard theorem to prove. It's the polar duality theorem. It says if you have a convex body, then the polar is the set itself. The forward direction is relatively easy to prove, depending on which you consider the forward direction. But the backwards direction requires what's known as separated hyperplanes, which we have here. So there is some hyperplanes in algebra, but here we define it in a similar way. A hyperplane with like norm u and constant c is the set of all y such that the dot product is equal to c. That's the hyperplane. And with less than equal to c, that's a half space, and like R2 is like something a little down here. And this is like the boundary of that there. Okay. So what we want to look at here is you can define every element in your convex body, convex body, a set x, which is equal to this, and what do we use that for? A little proposition, I believe this was formally going through the lectures, just because this is similar content, is that you can define your actually, this would be similar to what's going through the lectures. You can define your polar of your convex body is the intersection of all these sets x, because you need to hold for you need to hold for all x. This is like an equivalent way basically of writing the condition of the polar, which we talked about before, like by definition, which was on here, but this one here is an equivalent way of writing this Sx construction. So you can say, polar is equal to this. So it's pretty clear from that what do we say here? So it's pretty clear from this that if what would I say? If x is in k, then it's pretty clear that x is going to be in k circ, the polar, because k circ would be then the intersection of all y in k circ, such that this should not be. That should be right. Okay. And then let's use z in Rn such that z dot y is equal 1. So we effectively want to show that if x is in k, then it satisfies this condition, which is true by definition of such y, which we know that y satisfies that condition for every single x, so in particular it's going to satisfy that for your particular x. Whereas the hard part of this proves effectively just by hands a little bit k is a subset of k circ, and you want to show that it's not this separated hyperplanes infrastructure theorem can be used to prove that k circ is subset k. Proof is in lecture slides, but in terms of this theorem is that in terms of defining what a separated hyperplane first is, instead of a hyperplane given by this, which is C here I suppose. Is a separated hyperplane of a position vector p and your convex body k if the dot product is less than equal to c for all elements within inside your convex body, whereas the dot product of that element outside, this p outside, is greater than equal to c. Well, I guess p doesn't necessarily have to be outside, but for the separated hyperplane theorem it does have to be, so p has to not being k, and you say that you specifically want the separated hyperplane theorem it to be strict equality here. Like there's a little gap, I guess you could say, in terms of the hyperplane you're looking at and the c. And you can use that as we can like see this is looking something like a hyperplane. You can use that there to prove that And the big theorem that we want, which is in R n least, K circ is equal to K, which is quite nice. Okay. So the dual of the dual is, so the polar of the polar is equal to the set itself, which is true in R, not necessarily true in more generalized spaces. Revision on the algebra, I'm sure you're familiar with this. This is a little algebra here, determinant is equal for the transpose. In terms of like what we're about to look at, which is the more volume belief, what you mean is that if you have some sort of mapping by matrix A of your set that has a volume omega. We don't like define volume in this course, but we say like we have this like black box that can give you the volume of omega. Then you can talk about how that's transformed, how that relates to the volume with your dual, your polar, sorry. And also, I guess when you have like relatively simple sets such as circles, circles, then your volume would just be the area of the circle in how it works intuitively. Whereas what I meant is that you don't define rigorously what this volume is. You just say that it works in the way you expect it to in terms of normal sets such as like rectangles and tetrahedrons and so forth. But when you generalize it, it becomes more complex. The key other thing to know, as I said before, all linear maps are continuous. It's quite a nice property. And you denote the set of linear maps. Yeah, the linear maps are the matrices. Okay? In terms of finite dimensional space. This is the theorem I spoke about earlier. I did write it in a way that had the inverse on the inside and transpose on the other, but they are equivalent if I remember correctly. So yeah, AK is a convex body with its polar being this, which you can prove just by using that definition we talked about all the way up here. What was it? This one here, you can prove it through that definition, at least in one direction, and the other direction is a bit more tricky. Okay, and I guess we are walking through this a little bit. So prove that AK is also a convex body. We had a little bit on this on one of the other slides, and I told you a bit about how to do it. This is what I was talking about. If you take 2 points, you can show that since A is linear, this also has the long lane AK. If you just take the line from X to Y, you know that has to be in K, so it has to be in the image, which is also the same as lambda A, I think it's something like that. Yeah, lambda AX and lambda Y, one minus lambda. Yeah, so X dash Y dash is also in AK, so you can read through the details. That's not too difficult. This part at least. The hard part is the essentially symmetric part is also pretty simple through the fact that A is linear, so bring out the negative scalar. The hard part is the compactness, but I guess you could use the fact that since A is a continuous function, it preserves compactness. The part that is missing though is the bounded load, which you also need to prove. Bounded load, since you know that there is a ball of radius c within K, so that what do we say? The problem is if A is not orthogonal, then you don't necessarily also have a ball. So what you need is that it doesn't argue well here really, but effectively you want to use this property, that there is a ball that is a lower bound for your convex body to say that when you map, when you look at the mapping A of BC, that's also going to be a subset of A K. Yeah, AK. But you want to say that since, I guess you could argue since this is a compact set, I guess you could say, if you talk about the closed ball, this would also be true even if the definition of bounded load does use open balls, but you can still say this because this would still be true because of the fact that K is closed. So if you have an open set within K, then its closure has to also be in K because K is closed. And so you know that the mapping of A and B, this is also a compact set. And so that compact set is also compact sets have that argument doesn't hold either, does it? But you would want to make a connection between that being a compact set and some sort of ball of a particular radius. But we might come back to that. I don't think we won't come back to that. Okay, so the molar volume is the product of the volumes of K and its polar. Why is that cool? It just looks cool, is my answer. So this product, I guess, represents how large overall, I guess. So two factors at play. Some theorems you have is that the molar volume of the polar and your convex body are the same, because you can just like flip around the circle here, because double star equals the same, because you know that K double star equals K, so they're the same. That proves this right here. And you could also say that when you use a linear map to your convex body, then it's the same as the Moore volume of your convex body originally. Okay. Yeah, we say MK is the Moore volume of the convex body K. Alright, so we have a little question on that here. We want to prove first of all that K is the convex body, we want to find the polar of K, and we want to express the Moore volume into I1, I2. So quite a long question. So we try to visualize the set K over here. Okay, I'm quite screwed with time. Visualize like this. So some sort of set like this. Yeah, you would have seen something similar in the tutorials. You can argue that it's convex body by first argument it's convex, centrally symmetric, and so forth. You want to cover all the boxes there, you know, kind of look at it by inspection. Probably the better way to do it though, you can notice that this is the, since it's less than equal 1, it's the intersection of the, K equals the intersection of the ball of radius 1 in the 3, the P equals 3 norm, and the ball of radius 1 in the, since this is going to be true only in the first and third quadrant, then this becomes the negative here becomes like a positive, so it's like the sum of absolute values in that case. So this becomes the ball of radius 1 within the L1. Okay. So it's an intersection of these two, and closed balls, I should say. They're both closed. And so since these two closed balls, they're like the classic example, closed balls are classic examples of convex bodies, the intersection is also going to be a convex body, which is something you can prove, because you can like take the smaller of the two lower bounds and the larger of the two upper bounds for the bound above, bound below, closure following from intersection of closed sets that are closed, and the essentially symmetric following from these to be essentially symmetric. Okay, that seems good. Find the polar of K. So in terms of finding the polar of K, the trick you use, you might have seen in the tutorials, with this in this case where you're dealing with the intersection of different norms, basically, different convex bodies, is you take the, in each quadrant, like you take the dual norm of that respective norm, and you look at the associated convex body of that. So for instance here, in the second and fourth quadrant, you're looking at the P equals 3 norm. So the dual of that is, you're looking at over 3 plus 1 over q is equal to 1. And so that's 3 over 2 is equal to q. So that's what we do in the second and fourth quadrant, whereas in the first and third, you're looking at the 1 norm, so that would become the infinity norm. So what you would say is that it's defined as this polar, in just doing it quickly, would be defining as the sets in 2, 4. The convex body would be defined as x, we write it as 3 over 2, so that's equal to 1 in the first and third quadrant, x infinity is the maximum of x, maximum coordinate of x is also less than 1. Okay. So if you get this in the exam, you would have to, of course, prove that a bit more rigorously, but the intuition does motivate what you do have to do. Okay. Alright, so you can look at this here. Right, so in terms of proving that it is convex, they do what I said I did, which you take the intersection of two convex bodies, and then that proves that it is convex. And then you can argue the essentially symmetric part, similarly, and also the, well, I guess from definition a bit more, and closure from intersection of two closest is closed, compact from compactness and upper bound, lower bound from the upper bound, lower bound. You have K1, K2. This is effectively what I said here. You break it up into the two different quadrants. You can review this in your own time. Oh, and the last part I forgot, the molar volume in terms of I1 and I2. Okay. So what we're going to do is express the volume of this set in terms of I1 and I2 and multiply that with the volume in terms of these two, which we can write in a similar way. So let's write this one. That would be the square shape. And this one would be the, that's a bad drawing. Something like that. Where like this line, say, 3 over 2 is equal to 1. And this is just 1. Like that's 1, that's 1, so forth. So the volume, if we say the volume of K circ, that's going to be this volume and this volume add up to 2, and then you're plussing 2 of like the integral of this area to integral from 0 to 1 of the upper part, I guess, so your y in terms of x. Well, you're saying that x 3 over 2 plus y 3 over 2 is less than equal to 1. And so you can rearrange that for y. So you get an expression for the volume, and then you'd eventually do a bit of algebra multiplying it. In the interest of time, I will not go through all that. But you can effectively rearrange for y. You get this integral, you have 2 with them, you get 2 I1s. For the polar, likewise for just K itself. You have I2 here. Pretty sure that was I2. Yeah, I2. Okay. So many typos. I2. Okay. And it becomes this product here, if that makes sense. Yeah, and this one comes from the area combined in those two. What should I write? These two parts here. The two triangles. And the other one comes from the ball, the P was the ring ball on the quadrants. Okay. So yeah, you can review that. Alright, so we can basically skip over this chapter, the prime numbers chapter, because it's quite badly, short, and also there's not much to it in terms of nice analysis. Apparently it's never really shown up in the exam, so it's not too good. You can use Euclid's argument to prove that there's infinitely many primes by constructing, by contradiction, a new prime. So it turns out, like in more generality, that if you take all the primes up to n, and this is going to be a prime, so that is kind of used later in a few other proofs. But yeah, just take the word for it. That for most of the exams, you just kind of have to take the word for it, because they do show up in the exam, and that's a bit unfair, because they do, like a lot of these theorems in proofs given in lectures do involve a lot of sums and a lot of inequalities, but that would be unfair in the exam. You'd expect. The takeaway though here, as I said, is to look at the product of primes up to a certain I guess index of primes, so if you first k or first n primes, then this is also a prime, and you can use that, you can prove that, I guess directly, so that's not divisible by any of those first n primes, and so it has to be Actually, it doesn't have to be prime, but it has to be at least no less than the n plus 1 prime. So you can say Pn plus 1 is going to be less than or equal to this. So either this is a prime, or there's a prime between this Pn and this number here. And that's using the theorem on the next slide, one of the theorems. Not that theorem, like the theorem between them in terms of the growth. That's in the left side. It's quite a weak bound, but it does work if you want to look into it. Of course, like prime is divisible by any other number besides itself and 1. 1 is neither prime or composite. Pi of x, just to be familiar with the notation that might show up in the exam, is the number of prime numbers not exceeding x. For instance, pi of 5 is 2, 3, 5, not 4 Joes. And then you do the same for pi of 10. Yeah. Is this right? Yeah, 7, and yeah, 7 would be the additional one, because 9 is not prime, and any even number of 2 is not prime. Oh, this is the theorem, I'm pretty sure. Yeah. So this is the theorem that uses this, the fact that the n plus 1 prime is less than equal to this product of all the first n primes plus 1. That can be used to prove this result, which is, doesn't really tell you much, because this is quite a low growing function, to be fair. Not very helpful, but it is a bound, so as an analysis people apparently like that. The prime number theorem is a bit more powerful. Proof left as an exercise of radio's course apparently though. What it says is that you have this little function called lie, which is the integral of log to t from 2 to x. It says that the function pi of x, which gives you how many primes there are less than equal to x, is asymptotically equivalent to lie x, which is quite nice. If you ignore the little error term. But yeah, quite nice in this way. Yes. Okay, cool. Alright, so the real numbers. We have how much time? We still have time, at least. So let's start on real numbers, which are quite cool. So starting off, you have to remember the definition of Cauchy sequences. Cauchy sequences are sequences such that the sequence elements get arbitrarily close to each other as you go on. And so you might think that they always converge. That's true in R, but not necessarily true in other norm-vector spaces. So this is the definition of Cauchy, and some properties is that the sum of two Cauchy sequences is also Cauchy, product of two Cauchy sequences is the product of your sum is also Cauchy. So say if you want to prove the sum is also Cauchy, you can do that by you do the usual trick, getting your epsilons over 2s, and you use your triangle inequality to get an upper bound on the sum if you break between your x and using the fact that each sequence is Cauchy, you get an upper bound of epsilon over 2, break up your sum into the sum of the two sequences into the different parts, because you're looking at you're wanting the xn plus yn minus your xn plus yn. You want that to get small, because that's like one term in the sequence, that's another one. When n and m are sufficiently large, you want this to become sufficiently small. So you let your n be like the maximum of n1, n2. Effectively, you might have done a similar argument such that this condition holds. So that's when you split this up, you can use your triangle inequalities, split this up into two terms. You have one upper bound for each of them, and so in total you have a bound epsilon that says upper bound with a small number you can make arbitrary. Alright, monoids you might have forgotten by now. So they are basically, so we care about this in relation to R. What a monoid is in more generality is basically a group just without inverses. It also implicitly, if I remember correctly, does have closure though. So an example is that the group, this set R together multiplication forms a monoid. So that may be helpful for some reason, that kind of random term that shows up in the exam. What we define as a ring is where we have a monoid, and also the distributive laws hold. So an example of that is set apart by our matrices, denoted R and by N. just the trivial ring are itself and the quaternion groups. So quaternion ring. Yeah, I think that's fine. Yeah, so just you have that extra relationship between the addition groups. So you're getting closer and closer to a field. A field has its addition group and its multiplicative group, but you're not quite there yet because you don't have really inverses perhaps. Whereas a field is where you do have inverses, except for when you get rid of the zero element within your what's it called? Your field. Well, you know now it's a field, but you're previously ring. Okay, so order fields, you've seen this before in the second assignment, where you can say, you can kind of imagine all your elements on a line. We have some sort of element here x, you have an element here y, z, you can compare them, say x is less than equal to y, less than equal to z, so there's always a way to compare. There's always one condition or the other, so either x is below y or it's above. Okay, so you can place them more effectively on a line, and both can't happen effectively, so this is exclusive or, because otherwise if they both happen, then x is equal to y, so that these two kind of combined imply that x is less than equal to itself, which is kind of what you need. Transitivity holds, and also if you add constants, similar to the real line, if you add a number to both sides, it holds, and if you have a positive number, it also holds it. If really how you deal with inequalities in year 11 and year 12 math. So when you have this ordering on a field, that is a specific type of field we call ordered field. So you can maybe think about how finite fields, for instance, can't be ordered because you can't, in finite fields you have a specific number of elements, and eventually you have the sum of the identity be zero. Like for instance, if you look at the field z to p, which I believe all finite fields look something like, or polynomials over z to p. In that field you have like the sum of 1 p times is equal to 0. So you can like effectively in this field here you have 0 is less than this sum, which you can't have, so it's not valid. Says p not ordered. Whereas nicer fields such as our real numbers are ordered. So moving on, we have the Archimedean property, which you've seen in your assignment, which says that in terms of our ordered field, there exists some sort of natural number. So the natural numbers are always like, there's a subset in every ordered field that's isomorphic to the natural numbers, and like contains 0 and 1. In this case, there's always going to be one of those natural numbers that is greater than any element in your field. Okay, so that's property, which is about the least upper, greatest lower bound before, you can also the least upper bound, which is the upper bounds, or the number that is less than equal to any given upper bound. Right? It's like the largest number such that it is no larger than any upper bound. So you can think of it as like a lower bound for the upper bounds, quite nicely. You can see it's defined here. So that may or may not exist in a more general sense. But if you have an ordered field with what we call the least upper bound property, which is a nice property that we want, then you can say that every non-empty set with an upper bound has the least upper bound, which is very, very cool for us, because that is what we want effectively to have. Well, you see the assignment implies the Archimedean property. And I think I have something next slide. One of these. Yeah, this one, which we'll talk about. First of all, let's just briefly define the numbers, just for fun. So the real numbers are really just the set what you can define as the equivalent slices of Cauchy sequences. But another equivalent way that was focused more on in the slides in this course is the data cuts. So what a cut is a non-empty set of rational numbers such that it's not equal to the rational numbers. It's closed downwards, so if you have an element, then you have all the lesser elements. So you can imagine like you're cutting Q's like dotted throughout. But if this is like Q, if you have some sort of cut here, that's where they cut. Then you have all these elements here, this one, 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 and so forth. The other nice property, an important property, is that you need to make sure that this cut does not have a greatest element. So there's always going to be an element greater than any given element. You throw it someone, so I give you an element within the cut, you can give me, you give me an element in the cut, I can give you back one that's larger than it. If you're familiar with the Allen-Stone epsilon delta analogy. If you're not familiar with that, you're going to enjoy 2-1. In term 1 is quite a nice analogy that I unfortunately don't have time to go into. So the intuition is divides Q into two halves, where there's not greatest. So it can do something like this, less than 1, or is cube less than 2. A lot of wacky things like, don't assume that it looks nice like this. You can have some nonsense going on in the way you define the cut, like you can have an arbitrary cut. Okay, so you can define them to make a field, so that's our real numbers, the real numbers are, as I said, predict cuts. They can form an ordered field specifically, where you say that x is less than equal to y, when x is less than y, we're saying x and y are sets, and we also have that satisfies the least upper bound property. We've specifically, you can be constructive about that in the sense that your least upper bound, predicting cuts, is going to be the union of all of the cuts in your set, which turns out to also be a cut. If you don't know what I'm talking about, there is an example on one slides about that. First of all, just a little bit more analysis linking back to Bolzano-Weierstrass in the case of R. Okay, so what we have first of all is, if you're doing 2-1, just advertise 2-1 at this point. Allen-Stone gives an excellent proof of this, you can see. I think it's also done in tutorials, but Alan did better, might be. Alan's good, but he's not everything. But yeah, you can prove that every sequence of R has a more intense subsequence by looking at what Alan describes as the peaks of the sequence. Like, look at all the peaks. Very nice. And then you prove by conjugation there's not infinitely many peaks, because there's infinitely many peaks. Get in the way. And so that says, like, you can find the increase and a decrease in subsequence of R, and you can also argue that and the theory here that says every increase in subsequence of R that is bounded converges to its least upper bound. So if it's not bounded, you can just go into infinity, so you don't want that. So the consequence of that is that every portion sequence of R is convergent. So the way you prove that is by saying that if you have a portion sequence in R, then it is bounded. If it's bounded, then it converges because it has a increase in subsequence. Pretty nice, right? And that is exactly what the Bolzano-Weierstrass theorem says, is that in every non-empty, or in the case of R, every non-empty subsequence, every bounded subsequence in R, every bounded sequence in R is a convergent subsequence. I guess this is related to that. Not exactly. That's what I say here. I guess you have to argue in this case that if you have a subsequence of portion sequence that converges, then the overall sequence converges to that same. Whereas Bolzano-Weierstrass effectively relates to these two more. Because of the bounded nature, which also these are independent. So as promised, what is the least upper bound of your set of Dirichlet cuts? That turns out to be exactly the union of all of the cuts in that set. So like there's two parts to this, like for that to be well defined, like you want to say like your least upper bound is an actual real number, right? So you want to say that the union of a bunch of different cuts is actually cut itself, which does turn out to be true. And also you want to argue then that it is an upper bound in the sense that it's the supremum in the sense that you can't find an upper bound that is less than that by saying that like your union contains like all the elements, so it's necessarily going to be a superset, and so it is itself going to be an upper bound. So you can go through the details here. In the interest of time, let's skim over them. The key argument, though, you want to make is you want to go through the properties. You need to make sure that it's not empty, it's a union, it is not R because each of the cuts themselves have an upper bound of some sort of rational number. So if you take the union of all of them, you take the union of all the upper bounds effectively. Yeah, I guess that's harder to argue, but that does follow. And also the following down, the close down probably follows from the fact that it is a union quite nicely. And looking at if it had a maximum element, what you effectively argue is that means that one of the cuts you're taking in the union had to have a maximum element, which is a contradiction. So that's why the union can't have a maximum element. And then looking here, what we do to show that it is a what is the supreme of this union? Is that the supreme? Now we know it's a cut, we'll say it's the least upper bounds, which shows that any non-empty subset of elements in R, which we're saying R is the set of different cuts, has the least upper bound by this. Since we can argue that it has to be the least upper bound because there was a what do we say? Well, clearly, first of all, that it is going to be, well, first of all, greater than equal to any element within the this union is going to be greater than equal to any element in this S instead of that it can cut between the union over, so it is at the very least an upper bound. So what we have then just have to look at is in the case where there is a smaller upper bound. So if there's a smaller upper bound than this one, then you can argue that the problem with that so if you argue that M is an upper bound for S as well, you can say that since by definition all elements in the decaying cut have to be within M, that would mean that the union would also have to be within M. And so that would mean that what we define as our union has to be a subset of M. Right? I guess the way I was trying to prove that in my little head there was you can argue if there's a by contradiction, if this is not the least upper bound, it has to be a subset of this, that is the actual least upper bound, in which case you can find an element that's not included in the union, and then prove that by contradiction that doesn't mean it's a upper bound of the set. Or like, contradicting that it is the limit of the upper bounds. Yeah. Okay. Right, so what we want to look at, actually no, I should clarify, I did make a few verbal mistakes. Yeah, your least upper bound does actually have to be an upper bound. So it's not like the limit of the upper bounds, like I was saying. That's silly of me. It is, it's definitely an upper bound itself and also the less than any other, or less than equal to any other upper bound. Okay, so we'll just rerun this last part. So what we're looking at now is absolute values and numbers. So first of all, what we're interested in is what's called a multiplicative valuation. So this is very similar to a norm. It has the positive definiteness. It doesn't have like scalar multiplication, so in that way it's different to a norm, but it does have like this multiplicative structure. But it doesn't have triangle equality. What we look at in this course specifically is the p-adic valuation Q. So for any prime number, we can define the p-adic valuation of it, define the p-adic valuation of 0, 0, which we need here, and otherwise we're going to say it's not going to be equal to 0, specifically we're going to say it's going to be p to the negative a, such that number n can be written as p to the a times b. Okay. So we say when we have then that defines it well for an integer. When we have a rational number, then we define it as the quotient of the p-adic valuation on the integers. So p-adic valuation n divided by n. Okay. So in this case, we can find. Let's scroll. It's not letting me scroll. Why is it being difficult? Oh, there we go. Okay. So for these examples, say for instance, 9 is equal to 3 to the power of 3, no, just 2. And so this is equal to, in this case, we're going to p equals 3, p to the power of 2. So we're going to now 1 over p to the power of 2, so that's 1 over 3 squared, which is going to be 9, unless I'm being silly. Yep. And likewise, you can like that for these other numbers. In this case, this one is 1 over 7, remember correctly? Yeah, because everything. You're going up to 7. Yeah, so 6. Yeah, 7 doesn't find 6 factorial, just make it 7. So that's your expressions like we saw in the previous slide. So you have the 6 factorial here, and the 7 to the 1. In this case, it's 7 factorial. And likewise with 54, you bring out the 2 here to leave the 3 to the power 3. So you have 1 over 27, which is 3 to the power 3. Okay, so you also have this ultrametric property when you're dealing with periodic evaluations, which gives you like the triangle inequality, but it's much stronger. It says that it's bounded above by the maximum of the periodic evaluation of x and y, and you have equality if these two are not equal. No, that's not saying, is it? You would have equality when... No, obviously it's going to be... actually, you do have equality, so when... I'm just thinking of the equality. Yeah, when x to the p is equal, not equal to y to the p, then this becomes straight, as in x plus y to the p is less than equal to... strictly equal to max x to the p y to the p is the inequality you need there. Okay. And yeah, you try to find an example for that when you're dealing with this arbitrary p. So if you let's say x equals p squared and y equals p cubed, like what we spoke about earlier, when they're not equal, the periodic evaluations are not equal, as in this powers are equal, then actually will turn out to be correct. Because what you look at is x plus y will be p squared plus p cubed. P obviously does not divide this, so then you're left with the sum is equal to p to the negative 2, so that is also the maximum, and that turns out to be right in this case. Okay, so we talked about equivalent norms. You can also define what it means to... what is this? That's wrong. Is that wrong? That is not what I meant to write it. There's just a typo there. So yeah, two norms is going to be equivalent if for all x b of x is between some upper and lower c of x, u of x, and c of x, c of x. And as an example, if we made, if we put in a lambda here for our periodic evaluation, actually is this correct? Mine should be, or did I actually forget what the actual lecture slides say? Do you remember? Okay, hold up a second, hold up. Should probably prepare this more. Okay, just take a word for it then. Fix up the slides. We're never done. And then you get this theorem that says that QP is with the periodic evaluation is not Archimedean, so that's like different to what we said with this case of the group of numbers, and it turns out that every non-trivial absolute value Q is either the normal absolute value or the periodic absolute value, which is pretty cool. Alright, so this is where it gets a bit annoying, where you're talking about representations of periodic numbers. So you're familiar with representing your normal numbers as the sum of like your x is equal to your sum of k from k equals 1 to infinity of no, k equals, let's say, no, it should be from, yeah, you can say k equals negative n to infinity of 1 over 10 to the k times ak, whereas that works for your normal absolute value, but when you're dealing with p-adics, you need to go the other way, and you need to have the sum, which is like increase in the power of k for it to work out, because what we did was, effectively, it's like for larger numbers, effectively, we're making the p-adic valuation smaller, essentially. Yeah, because it works quite differently. So, if you have, say, this sequence, then it does not converge in Q because it gets larger and larger, so it's just increasing. But in QP, yeah, there's like QP here, with the rationals together with the p-adic evaluation, then you look at the differences between elements in the sequence defined like this. So the difference in the sum would be the additional terms, so either the power of n plus 1. So it does not converge in Q. In the normal absolute value, but it does converge in the p-adic norm, because what the p-adic norm, this would be p to the power of negative n plus 1. And then it converges. So what we say is that we can represent any p-adic number. I think I've got the next slide. You look at the p-adic numbers as its completion with respect to this type of convergence, pretty much. You say that the QP, the p-adic numbers, is completion of Q under the evaluation of QP. So instead of the normal like absolute value evaluation, we used to define the completion of the real numbers using the Cauchy sequences or the decline cards, but doing it differently here. So it's a different explanation, or a different way of doing completion of the p-adic numbers. Specifically, it's a set of all equivalence classes of Cauchy sequences of rational numbers, similar to what we looked at with, there is a way to define the real numbers as Cauchy sequences of rational numbers with respect to the normal absolute value. Okay. So the p-adic integers is specifically all the numbers in the p-adic numbers that have their p-adic evaluation less than or equal to 1. Whereas specifically what we define as, we define x to the p for like when x may not be rational as the limit of n approach infinity xn p such that x approaches xn, x minus xn with respect to p approaches 0. Yeah. So we use the limit there. Okay. Right. Okay, so we can try to determine the following belong to the 7 p-adic integers, basically looking at if they have the p-adic evaluation less than or equal to 1, so you can find the p-adic evaluation of each of them by, like, say this one would be p-adic evaluation of 7 over 11, that's equal to 1 over 7 over 1, so that's equal to 1 over 7, so that's less than or equal to 1, so that is. Whereas, say, this one is not, because you have the 7 here instead of 1 over 7, likewise with this one, 1 over 1, because none of these are divisible by 7, so it's not, oh, it is. And, okay, so every p-adic integer is the p-adic limit of a sequence of integers. That's a nice result. You need to then work with this canonical p-adic expansion. So every p-adic number has a unique p-adic expansion in this form from negative r to infinity. Similar to like our decimals with ak between 0 and p minus 1, and we'll look at an example finding that in a couple of slides. And it's in ZP if and only if, like similar to like it's in the integers if, well, it's like in the non-integers for like the real case of the normal normal real numbers. In this case, we said that we know that it's in the p-adic integers if and only if it starts from a number that is non-negative. So there's no negative R term, it's always starting from a positive power p. So when it looks something like this, then it's a p-adic integers. So it looks like an integer if you're talking about like convergence, pretty much in the Vega terms. Alright, so we'll look at a question here. You can write down the standard representation, which the first part wants, like this, where you want your AK between 0 and p minus 1, so just like using the same idea as decimals, but flipping around. We want to look at if this converges, so an is equal to sum k equals 1 to infinity in k factorial. We want to look at if it converges in q to the p. So what we need to look at then is, say, an minus a for some a, perhaps. So, or maybe like the differences between terms. So just first of all check if it's Cauchy, because if it's not Cauchy, similar like with your real numbers, then it cannot converge. So this is less than, it's specifically equal to n plus 1 factorial. Actually, what's this n? Right, and that would have, that would, what's like the precise sign you could use? That is equal to p to some power. And you can say like if n increases, then this power a increases, specifically like it'll be related by logs in some fashion. You can say like that's, with respect to p is 1 over p to the a, where a approaches infinity as n approaches infinity. You can make that type of argument. Let's be more precise here. So that would say that at least this sequence is Cauchy, and since it is a completion of the set of rational numbers, every Cauchy sequence will converge. That's the idea of completeness. So this sequence will also converge. Not that I really know what it will converge to. But yeah, you can make that type of argument. And you can also, this does go into detail about what happens when you don't just consider consecutive elements. So when you have some xn minus xn, you look at all these terms, but you can apply the algebraic property here in a similar fashion. So you can say the n factorial in the PA evaluation of that, which is 0. So the sequence is Cauchy, and so converges. Because the idea of the word complete in terms of a vector space means that every Cauchy sequence, normal vector space means that every Cauchy sequence converges. So when we say that we can complete the set of rational numbers with respect to the p-adic evaluation, then we're saying that we're making every Cauchy sequence converge, because we're saying that p-adic numbers like the equivalence classes of Cauchy sequences, effectively. So it does work like that. Yeah, so you can, at least k factors, you could say if n is greater than equal to p to the k is the way you can make it precise like that. Alright. Okay, cool. Right, and then we just have a little last example. This is just following similarly on what's done in lecture slides about finding the five-adic expansion of 2 over 3. So basically what you're looking to use the benzoate identity here. You want to use your prime, which in this case is 3, and you want to use your denominator, which in this case, so your prime is 5, your denominator is 3. So you're starting with your number and you're replacing a 1, which is like this 2 times 1 numerator. You're replacing that 1 with this expression here, so that you can write, split it up, you cancel out 3s, you in this case you'll have a 4 on the first term, and then you still have a 5 here, so like you're going upwards in terms of your powers of 5. So this is just, this is very similar to the algorithm you would use usually when you're trying to find the decimal expansion of a number. It's just applying in this case we're going up, so it's a bit different than that. Use this type of thing. So this would generalize when you're dealing with more arbitrary values where you look at the denominator. You can also like factor out. If you look at like 2 over 15, which was done on the sides, that's going to be the same as 2 over 3 times 1 over 5. And so like this is 4 times 5 to negative 1 plus negative 2 over 3, and then if you like the periodic expansion, this is keep going with that. It's like, for instance, what you do, so it's like generalize, you have like larger powers here, so this is to the negative 2. Then you can continue, like you can see how the process would continue. For instance, here we continue it over and over. But like the little trick is that you make sure you have like each of your terms, like this one here is between b between 0 and 4. Otherwise it doesn't work out too well. Alright, so I have a little bit of mistakes to fix. I'll do that in my own time. So let's clarify for the video purpose, I guess. What do I put here? What silly nonsense did I put here? Do I have the lecture slides on hand? Might turn the audio off.
Someone else was watching you. When you got one more spectator.
Yo.
What's the other spec here?
Not the show, Miles, the understanding. This is the MATH2701 lecturer.
Sick. It's pretty young.
He is. He's also pretty. He seems chill.
It was just one on the 2701 chat out of nowhere.
He just spawned in, yeah.
Yeah, I'm like, wait, what? Alan spawned. Like, I can see him spawning in 2 for 1, but like, he used to appear out of nowhere just to say stuff.
I did this see like he makes absolutely stupidly difficult examples. Like, well,
The exam wasn't that
compared to
long.
me in my undergrad, I didn't know 2701 equations to prove that are only 3711. That's crazy.
Oh yeah, no one's on their YouTube account. Right, take their YouTube account.
Why did Alice Brennan bring out just to say I was more fucked than you? It's crazy.
So you still have the raw Brandon
I do.
For what?
money.
Money. Okay. I was right. This is some bull. This is
Thank you. I appreciate it.
Geometry.
yeah, this should be
Ah, less than or equal to
yeah.
B prime, B prime.
Like for God, yeah.
Different C's. Yeah. So this is what should be. Yeah, that's what it should be. Yeah, okay. And then this would be not a correct example? No, I don't know about that. Yeah.
And for the last example,
Mm.
how would you write the p-adic representation?
You just like do a trail of dots here. So the question was how do you write the periodic representation? You just keep going until you find sufficient many terms, then you trail it up at the end.
And then, what would you like write it in terms of?
In terms of what?
Like, you know how in the lecture it was like 4 times 5 to the power 0 plus 1 times 5 to the power.
So some repeat,
Yeah.
but not necessarily.
What would the sum be of this be?
Like you'd say it's like 4 plus 5 plus 1 plus 5 squared.
Yeah, I'm like, yeah,
Dot, dot, dot,
that's
dot.
fine.
That's what you could say.
Yeah, and then how would
Like, fair enough. It doesn't-
Like if your real numbers trail with decimals at some, right? Like you put a dot, 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 right?
yeah.
So you're saying it's like 4.5 dot, 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 basically. Until like P.
Okay.
Okay, I'll end the stream now.